Thank you very much, Bohong. So hello, everyone. Good morning, good afternoon, and good evening. My name is Jing Wang, and I'm a postdoc fellow in the Department of Mechanical Engineering at the University of Michigan. Today is my pleasure to talk about one of my recent work about a coating that repels viscoelastic solids for the application of water saving. So there's a lot of sticky problems in different phases of matter that exist in our household and industrial settings. So that's why there's a strong need to have repellent surfaces or repellent coatings. For example, for water splitting, we generate oxygen, we generate hydrogen on these reactors in the cathode or anodes. But these gases will accumulate and form a gas film that blocks the reaction, which further reduces the reaction coefficient. And another example is for heat transfer, especially for condensation. Once the water droplets coalescence, grow and form a film, the film will serve as an insulation layer, and this insulation layer greatly reduces the heat transfer coefficient. And not to mention about the fogging that happens on the cars and also happens on our PPEs under this pandemic, on the goggles, on the face shields, and also in the like oil and gas industry. That's the drag creates and accumulates on the pipelines, and also the bacteria falling in hospitals, marine biofouling in maritime industries, icing in airplanes, in aviation industry, or in cars, and dust contaminations on solar panels that reduces the energy conversion efficiency. So we can see that with all these problems, it's spanning from the gas phase to the liquid phase with nanometer scale to all the way to the kilometer scale. And also for like different solids with different modulars, like very soft biofilms to very hard ice and dust. So people have been studying the interface of how to reduce the interfacial adhesion back in like more than 100 years ago from the Young's equation. Later years, people, for example, the Casey-Baxter found out the Casey-Baxter relationship. And until very recently, like 30 years ago, in 1990s, the superphobic community have developed very rapidly. From the Lotus-Leaf effect that has the superphobic surfaces, from the springtail surfaces that creates these super oleophobic surfaces with this reentrant or double reentrant surfaces. And very recently in 2011, people inspired from the pitcher plants that has a slippery rim that creates this different strategy of liquid repellency. So take two, for example, the Lotus-Leaf effect, and it is summer now, and we can see this effect, the water droplets beats up on this Lotus-Leaf. And the reason it beats up because of this nano and micro hierarchical structures on the Lotus-Leaf. These nanostructures would greatly reduce the interact or contact with the liquid and solid and replace it with a liquid-air interface. So at this three-phase liquid, air, and solid three-phase composite interface, the friction and adhesion greatly reduced. And inspired by this, people have fabricated a lot of superphobic surfaces, for example, here on the silicon. And as the air, we replace the solid with air. The air is highly compressible and deformable. That's why it cannot stand very high pressure. So once we have a really high pressure interacting at this interface, will break through and transit from the Casey-Baxter state to the Wenzel state, which is a much higher adhesion state. So that's why, inspired by these pitcher plants, that using a very different strategy, that replacing these solids to air instead of to air, but to liquid, to another liquid. So this surface was invented in 2011 by my PhD advisor and his mentor at the time at Harvard, John Eisenberg, together. That they create this slippery liquid-infused power surfaces, short for SLIPs. So it composes three components. One is the underlying roughness solid surface, and the other is the chemical coating that has some better chemical affinity to the lubricant, and by capillarity force, the lubricant will spread and form a stable lubrication layer. And this surface can repel any liquid that is immiscible to the lubricant. So take two, for example. So for crude oil, is a complex hydrocarbon that can be repelled by slips, but cannot be repelled by this porous superhydrophobic Teflon, not to mention aluminum. And also can repel aqueous complex liquids like biological fluids like blood as well. So back to today's topic, how can we use these like repellent surfaces to solve one of the world's crises, which is the water scarcity. And water scarcity is becoming more and more serious in recent years. According to a report back in 2016, so 2/3 of the population on the Earth will face at least 1 month of water scarcity in the air, which is very scary. So people spend and researchers spend a lot of time focusing on desalination from seawater, collecting water from our thin air, from fog, and also reduce the water consumption in agriculture systems. But none of this focuses on our household settings. So 141 billion liters of water, fresh water, is flushed down our toilets globally every day. And 23 billion of liters of fresh water is enough to support the entire African population. So we flush down our toilets, the water that is sufficient to support the entire population in Africa for 6 days. So why we spend a lot of water to clean our toilet bowl? Because the thickness of the human feces to almost all the surfaces. This is a big problem. So let's take a look the previous introduced superhydrophobic surface. Can this surface solve this problem? So we tried with we test with superhydrophobic surface with our synthetic fecal waste. And you can tell that it's just adhere on the superhydrophobic surface. And we also use water. You can see this is superhydrophobic. We use a lot of water to clean, and also the area that's in contact with the fecal waste becomes hydrophilic. So can we use the state-of-the-art slippery surface, the slip surface? Let's do the test. We also test with this fecal waste, synthetic fecal waste. It performs much better, but still leaves a lot of residues on the surface and takes some water to clean the surface. So with the previous knowledge gains from so many brilliant researchers, can we start to think about how can we create such surface that repels this viscoelastic adhering fecal waste? So starting from the Dahlquist criterion. So Dahlquist created this criterion for 3M when he was working in the 1960s. So basically it tells us when a pressure sensitive adhesive, which is a viscoelastic solid, has a storage modulus less than 0.3 megapascal, it can conformally in contact with any surface roughness. So which means increasing the surface roughness will increase the adhesion once the storage modulus is below 0.3 megapascal. And our viscoelastic solids, the fecal waste, is below this criterion, which means in order to reduce the adhesion, we need to reduce the surface roughness. And the ideal surface will be a ultra smooth surface. And secondly, not only to reduce the surface roughness, we consider the adhesion energy, which is the work of adhesion multiplied with this function, which is physical parameters and environmental parameters. So we focus on the work of adhesion. The work of adhesion can be expressed by when this viscoelastic solid is in contact with the solid surface and is under air, which is a 3. So it has the surface energy together is gamma 1, 2. So when we want to detach them, the entire surface energy state becomes gamma 1, 3, which is the viscoelastic solid to air, and plus gamma 2, 3, which is the solid surface to the air. So this equation can be further simplified by the good equation like this. So we only need to consider the the surface energy of a viscoelastic solid and the solid surface. And traditionally, there are two methods to reduce the adhesion. One is to lower the surface energy of the solid surface by salinization or polymer deposition through CVD or PVD. Another method is just by lubrication. So the lubricant can be generally absorbed by the viscoelastic solid and further reduce the gamma 1,3. So here we propose to stabilize the lubrication layer. In this way, we can reduce both gamma 2,3 and gamma 1,3. And so this adhesion problem becoming a cohesion problem in the lubricant itself. So we want to have stable lubrication to further reduce the work of the adhesion. So how can we achieve a stable lubrication on a smooth surface? So thermodynamically, we need to have the spreading parameter larger than 0 and the disjointing pressure larger than 0. So basically, we need to have the spreading parameter under air and under a foreign liquid or foreign matter, both larger than 0, and the disjointing pressure larger than 0. So here, A is the Hammacher constant, and E is the lubricant thickness. So this is always larger than 1. So we need to have the Hammacher constant larger than 1. So basically, we need to have the spreading parameter larger than 0 and disjointing pressure larger than 0 to have a stable lubrication layer. So based on this design criterion, we developed this two-step spray fabrication to fabricate a liquid-entrenched smooth surface called LES. Basically, we spray the first layer to create a PDMS grafted surface, generally have a thickness around 1 nanometer, and then spray the second lubrication layer, which is stabilized on the surface. And then we can use this surface to test whether, or this system to test whether theoretically or experimentally is valid. So theoretically, we calculate the work of adhesion and find out that the method 3 has the lowest work of adhesion. And we also measure the work of debonding and normalized with the glass, with the untreated glass, and find out that the LES coating, which is the third method, really has the lowest work of debonding. So let's see the performance. Compared to untreated ceramic, which adhere to the viscoelastic solids and takes a lot of water to clean, and our surface just slide off and doesn't take much water to clean the surface. And as we use a spray coating process, we can put the LES coating onto complex geometries and scale it up. For example, we put it onto a real toilet, and compared to a commercial available cutting edge hydrophobic glaze coating, it doesn't quite work, but on our surface, it just slide off into the center of the bowl and it doesn't need much water to clean. And further, we validate this low adhesion performance with our collaborators in the Cranfield University in UK. And they built up this testing setup. Basically, we drop the real human fecal waste onto the testing surface. And when it's impact on the surface, we release the holding pin and let the rotation momentum to remove the fecal waste. And let's see the results. So basically, it's like simulating the toilet situation and with a shorter impacting distance. And you can see the real human fecal waste is very, very sticky. And this time it's just gently attaching on the ceramic surface. And we release the holding pin and it just stuck on the surface. And we also test with PFPE, which is coated on our cooking pans, non-sticky pans, and also silicone, and which is widely used for biomedical applications. They all stuck, but on our LES coating, just slide off without leaving any residues. And most importantly, we also validate how much water they can reduce to clean the surface. And generally, they can save 90% of the water to clean the surface. So we test different solid contents percentage of the fecal waste. So 10 and 20 means it's kind of watery fecal waste, like someone has a diarrhea, and 30 to 40% is a healthy fecal waste, and 50 to 60 is someone has a constipation. That's the waste is a little bit hard. So because it's watery, when it's coming into the water, it doesn't take much water to the uncoated surface. So that's why you see not much a reduction of water saving, but intrinsically it's very easy to clean. So the problem is here, and we can reduce 90% of the water. So to summarize, we compare with superhydrophobic and super oleophobic surfaces. The fecal waste will be a solid to solid interface, and to slips will be a solid to liquid interface, but with very high contact area because of the required underlying roughness. And when we become less surface, the solid interface becomes solid to liquid interface and has a minimal contact area, and the performance is great. And we can also repel all kind of liquids, viscous liquids, and viscoelastic solid as well, has a dynamic viscosity spanning 9 orders of magnitude, and compared to all previous state-of-the-art surfaces is a great improvement. So to summarize, we have this design principle based on the Delquist criterion, adhesion theory, and wetting theory. And we fabricate this less coating, which has this viscoelastic repellency performance. And if we can apply this to the toilets, so we don't need to flush the toilets again and again to clean the toilet bowl. It just needs once flushing and use very minimal of water. So with that, I would like to thank my PhD advisor for this work, and all the other mentors and collaborators, and all the graduates and undergraduate mentees, and also the funding agencies, the Penn State and PPG gives the graduate fellowship, and also the EASF to support the core of this work. So thank you all for listening, and here are my contact information. Any questions you can ask if you don't have the chance today. Thank you.
Thank you. Maybe you can.
Anyone have any questions? Okay. Yeah, Wang Jing, I have a question. To my understanding, your coating is something like you grow the polymer brush on your substrate, and then this polymer brush will contain some liquid.
Yes.
It's okay. So your polymer brush so your polymer brush is kind of hydrophobic, right?
Yes. It's hydrophobic.
Yeah. So what's the type of your liquid?
Oh, the liquid is yeah. Sorry, I should mention that the liquid is a PDMS oil as well, so it has the best chemical affinity and will satisfy this criterion, basically.
Yeah. Okay. So because your polymer brush is hydrophobic and your liquid is PDMS, so the PDMS can be trapped in the polymer brush. Okay. So did you study the long-term stability of that coating?
Longevity of the coating? Yes. Due to the time issue, I didn't mention that. So the longevity, I will show it here as the backup slides. So if we only flush the toilet, we can stand like more than 500 flushes without losing all the lubrication. But if we have the viscoelastic solid impact and then clean out the waste, and generally can have like 10 times. So basically, if it is like used very intensively, you have to apply the lubricants each week or each other day in a household setting. And also to be mentioned, the first layer of the PDMS grafting is permanent, so it's covalent bonding. Only the second layer is as a functioning and also a sacrificial layer. So we can always reapply it. For example, if we have this PDMS grafted layer, it's kind of more sticky to the original, compared to the last surface. But if we just spray the lubricant, the function can restore.
Okay, thank you. Yeah, we got a question from Professor Yan Fecal, please.
Hey, very nice work. Because I learned a lot. So I'm curious about your reference to this viscoelastic property. So how does that play a role? And you particularly mentioned this magic 0.3 MPa viscoelastic storage modulars.
Yes.
And the human feces, is that also is that viscoelastic and with the certain storage modulars as you mentioned?
Yes, there's actually some literature. Only a few groups, I guess it's 2 groups, study the viscoelastic property of human waste, and they test the real human waste. I think they have measured very similar storage and loss modulars compared
But
to
the question is from mechanics point of view, talking about adhesion, talking about de-adhesion or de-icing or whatever the debonding, whatever names you are using, how is this viscoelastic behavior participate into this adhesion and the de-adhesion process?
Yes. So in our system, we consider 2 things. So the first is the 0.3 is just an industrial standard to use for like almost all surface roughness. But actually, it can be more accurately quantified by the surface topography itself. So basically, 0.3 is kind of a golden line. If below it, most of the surface would have the conformal contact. So we consider the adhesion only to reduce the adhesion. So we don't want to have any surface roughness. That's the first consideration, to reduce the adhesion. And second consideration for the viscoelastic properties, as it is a viscoelastic solid, it tends to absorb like a chemical, so it tends to absorb a lot of like lubrication or oils, like low surface tension liquids. So that's why we proposed here to have them to absorb some of the lubricants to reduce their surface energy. So that's the second consideration.
Okay, thank you. Yeah.
Thank you.
Okay, a question from Professor Ruobin Bai, please.
Hello, Jing. How are you?
Hey, good. How are you?
So I have a question. So from what I understood, you basically graft PDMS brushes on the surface, say a ceramic of a real toilet, right? So
Yes.
then you can reuse the PDMS solution to spray on it so that it can be reused for longevity. But then I think one scientific interesting interest is now if you have a silicon oxide bond, then especially with a lot of water, then over time we know from glass this can have stress corrosion or crack propagation over time. So for PDMS, you can expect a similar thing. Actually, I think someone has shown that. So my question is, when you flush it over time, for example, over half a year, 1 year, then some of the brushes may just fall off because of this, I don't know, maybe. Then did you see that, or do you foresee any way to solve this problem?
Yeah, that's a very good question. So I think for what you mentioned about the crack propagation on the interface of the PDMS is mainly applied for the cross-linked PDMS, which is a bulk PDMS, has much thinner, much more thickness. So here we used a grafted PDMS, which one end is covalent bonds to the subject. The other end is a free, is mobile. So it's not like the cross-linked one. But for the longevity, we do observe, not on the toilets, but on the windshield, like over, not half a year, it's over years, that still degrades. We don't know the mechanism right now because PDMS should be stable under UV, but we are using the brushes, which is made of silicone. So we don't know the mechanism of this degradation, but we think there are some drawbacks of using this one. There's some room to improve. We need more investigation on this.
Yeah, okay. Goyong, you have a question?
Yeah, very nice talk, Jing. And I have a question. Could I clean the toilet, for example, with a plastic foam, and will it affect the performance of your layer, your coating layer?
Yes. So the glass, the plastic one is very hard to coat with PDMS. We do have another patent to successfully grab PDMS on the plastics. We haven't tested the longevity of it. We mainly use it for like a ostomy bag for those patients, as they have to like eject their fecal waste outside their body, cannot use their regular system. We investigate on that application, not to the toilet. But I think for the toilets, for those coatings, our methodology will have a reduced longevity because of the intrinsic fabrication process. But that's a good point. This application is only for ceramic-based surfaces and can be expanded to some of the metals, but not all the metals. And certainly we need some modification of fabrication to expand it to plastics.
It is easy to get the PDMS away from the layer, from the surface, so I still thinking that we need a brush clean it, even you have this layer, right? Because some chemicals or something will deposit on the surface, or it will not happen.
Oh, you mean the brushes to clean the surface? Yes. We tested with so basically when we do the water consumption measurements here, so what we see is when we impact the fecal waste, it generally slide off or bounce off on our last coating. And when it attaches, the flow just move it very, very easily with a minimal shear. So I don't think you need a brush unless the coating is damaged. So it's and also better not to use a brush to avoid the damaging of the covalent bonding. So yeah, not using brush, but it should be efficient to clean the toilet.
Okay. Thank you.
Yeah, okay. Due to the time limit, our last question is from Sophie Wang. Please, this is the last question.
Hi, Jing. Hi, very nice talk. So my question is about will this technique apply to other situations? For example, underwater, we want to avoid anti-fouling. We want to avoid fouling, for example, the penetration of water into, for example, some devices or sensors. Do you think this technique will be helpful for these underwater situations?
Yes. So this is a good point. And for slip systems, they're already being demonstrated a lot by other groups using slips to prevent the marine fouling or underwater fouling with algae, with barnacles, with mussels as well. I think we have some advantages and disadvantages compared to the slips technology. So first, I would say the advantages is we may have an even lower adhesion, as we mentioned, to the barnacles and mussels because we have a smooth underlying surface. But it also causes the drawbacks of because we have only a nanometer thickness and 1 micrometer of thickness of lubrication. So the durability is very minimized unless the application can have some strategy to re-lubricate from time to time very frequently. Else the longevity will be a big issue for this situation. But for slips, since we have the roughness, underlying roughness can maintain a much larger volume of lubrication, which means they have a better longevity. Other methodologies, for example, using polymer networks to infuse with lubrication, will also help to reduce the marine fouling or other fouling in the underwater applications, but also maintain a pretty good longevity. And we here in the University of Michigan, we have a recent work that will be submitting very soon about this, that using a polymer networks that has a pretty good mechanical durability and also the longevity, and also has this functioning lubrication layer.
Okay, thank you.
Okay.